surds or radical, as you may call it, lesson 1 and 2 classwork correction. We want to look at the correction to the classwork under lesson 1 and lesson 2. So you have lesson 1 and 2 classwork. Number 1, list 5 rational numbers each under proper, improper, and mixed fractions. Number 2, list 10 irrational numbers. 10 irrational numbers. Number 3, list 10 perfect square numbers. Number 4, write each of the following as complete square roots, that is single form. Number 5, express each of the following in basic form. Number 6, you have simplify the following. So you have A and B there. So let's take the correction, the solution to these classworks. So number 1, list 5 rational numbers each under proper, improper, and mixed fractions. In lesson 1, we define a rational number as a number that can be expressed in the form A over B, but we use P over Q then. So I say the same thing, A over B, such that B must not be equal to 0. Of course, A over B is a fraction. So once you have this mindset that any number that can be expressed as A over B is a rational number where B must not be equal to 0, then you are good to go answering question 1. So under proper fraction, proper fractions, they are the group of fractions such that the numerator is smaller than the denominator. So you have fractions like 2 over 5, 3 over 7, 5 over 9, 1 over 6, 45 over 86 over 87. The list is endless. The list is endless. Then under improper fractions, these are the type of fractions such that the numerator is always larger or greater than the denominator. So you have 5 over 2, 7 over 3, 9 over 5, 6 over 5, 87 over 45. Under mixed fractions, we define mixed fractions as the fractions obtained when we add or combine a whole number and a proper fraction. So I listed all the proper fractions in the first case and attached whole number to them. That is 3, 8, 10, 4, 1. So the list is also endless. Okay, now you should understand that what I have here with your own might not be the same. In fact, it's not possible for us to have the same answer, but the bottom line is your answer should be in this form. So just compare your own with what you have here. Number 2, list 10 irrational numbers. One thing you should note is that irrational number is a number that their square root can never be a whole number. That is non-perfect square. Non-perfect square. With this mindset, you can list as many as possible. So some of them are root 2 to give you 1 point something, root 3 1 point something, root 5 will give you 2 points, root 6 2 point something, root 7 2 point something, root 8 2 point something, root 10 is 3 point something, root 11 is 3 point something, root 12 and 13. So you can never get a whole number when you take the square root of irrational numbers. Okay? Solution to number 3, list 10 perfect square numbers. So number 3 is like the reverse of number 2. A perfect square is a number whose square root is always a whole number. If you take the square root of a perfect square anywhere, anytime, you will always get a whole number. So such numbers are 4, you have 9, you have 16, 25, 36, 49, 64, 81, you have 100, 121. That is the first 10. There are others like 225, you have 169, you have 196, you have 400, 900, and so on and so on. Number 4, write each of the following as complete square roots. That is single form. So we reverse all these ones. They are in basic form already. You express them in single form, that is as a complete square root. So you have 3 root 5. First, 3 root 5 means 3 times root 5. So you are going to, for you to express in single form, the basic rules were told that different sort can be multiplied. The way it is now, 3 is not a sodic number until square root is introduced to 3. Mind you, anything you are doing, if you reverse it, it should give you back the original problem. The square root of a number that can give us 3 is 9. So we are changing ordinary 3 to the square root of 9 times square root of 5. Since you can multiply different sort, this becomes square root of 9 times 5, and that is square root of 45. Everybody should have this, no variation in the answer. 11 root 3 is the same thing. You have 11 times root 3. The perfect number whose square root is 11 is square root of 121 times square root of 3. Different sort can be multiplied. So you have square root of 121 times 3, and that is square root of 363. So this is a complete square root. There is no number attached to it to the left, none to the right. C part of it, 10 root 7. That means 10 times root 7. The perfect number whose square root is 10 is 100. So you have root 100 times root 7. You can multiply different sort, that is root 100 times 7. So you have root 100 times 7, and that is root 700. That is a complete square root or in a single form. All our answers should be the same with the one I have. There cannot be variation. Number 5, express each of the following in basic form. In basic form, root 512, root 648, root 363. In lesson 1, we look at basic and single form, where I told us that for you to get a basic form, it means in that single form there is a factor of the radicand. Okay, a radicand is the number under the square root. Okay, So there's a factor of the radicand that is a perfect square. And I told us a simple trick of doing that. That simple trick is you divide 512 by the first irrational number, that is 2. Then the answer you have, you try to see if you can get its square root and it's a whole number. Okay, so let me show us what I'm talking about. So okay, this is what I'm talking about now. So I'm going to divide 512 by 2 first. So I'll have 512 divided by 2. So equal to, what I have is 256. So I'm going to check if the square root of 256 is a whole number. So I'm going to invoke the square root sign. See now, what you have there is 16. So what you have is 16, so there's no need of dividing again. It is when you have a decimal number that you try to divide by 3. Okay, so we take 256 times 2 will give us 512, since 256 is a perfect square. All right, so let's continue. So you express 512 as 256 times 2. So if you split it down, you have root of 256 times root of 2. For 256, the square root is 16 times root 6 times root 2, which is an irrational number. When you multiply, you have 16 root 2. 16 root 2. Okay, the second one, 648. If you divide by 2, you have 324 times 2. 324 is a perfect square. That means its square root is a whole number, and that is 18 times root 2, and you have 18 root 2. So let's check 363. So let's check that. Okay, calculator is here now. So let's clear it first. So let's start with 2. 363 divide by 2. So you have 181.5. This number is not a whole number. That means you can never get its square root. You have to try 3, the next irrational number. So you have 363 divide by 3. What do you have there? 121. So let's find out if this number is a perfect square. You simply look for its square root, and you have 11. So the meaning is that what can replace 363 such that one of the factors is a perfect square is 121 times 3. Okay, so let's continue. So we have 121 times 3. If you split it down, you have root 121 times root 3. Then you have 11 times root 3, and that is 11 root 3. All the answers need to be the same because we are solving the same problem. There should not be variation in the solution. Okay. Number 6, simplify the following. This addition of surds, and I told us that you can only add similar or like surds. For that, when you have a problem what you do first is to see if you can obtain similar sort from the respective radicand, that is 12, 18, 72 and 75. To do that, you express the radicand in basic form such that you look for a factor of each radicand that is a perfect square. So for 12 you have 4 times 3. For 18 you have 9 times 2. For 72, 36 times 2. 75, 25 times 3. Square root of 4 is 2, so you have 5 times 2. Square root of 9 is 3, so you have 3 times 2. 3 times 3, root 2. 36, you have 6, that is 4 times 6, root 2. 25, you have 5, that is 2 times 5, root 3. When you multiply the constant or the coefficients, you have 10 root 3, 9 root 2, 24 root 2, 10 root 3. Now we have a similar sort, although not all. So the ones that are similar, let's bring them together following ascending order, that is 2 before 3 now. So we have 9 root 2 plus 24 root 2. Then for rational number 3, you have 10 root 3 plus 10 root 3, and that is 33 root 2 plus 20 root 3. 20 root 3. So the idea here is to get similar sort from the radicand. Also in lesson 2, addition and subtraction of sort, we find out that there are times such that after you express the radicand in simplest form, you still have different sort. In that case, you stop at that point where you cannot add nor subtract the different sort. Then B part, you are asked to add and subtract. This problem is already in simplest form. If you check very well, the similar sort there, you have 3 root 2, then root 2, minus 2 root 3, minus 2 root 3, plus 2 root 3. And you should know that minus 2 root 3 plus 2 root 3 is 0. So you are left with 3 root 2 plus root 2. You know there's 1 here, invisible. So 3 root 2 plus 1 root 2, you have 4 root 2. So if your answers to the 6 classworks, if they are all correct, you clap for yourself, mark for yourself, and be faithful in doing that. Don't go and change anything because the tutor is not seeing you. Do it faithfully. If you make any mistake, you correct yourself. That is the essence of the classwork, to see if you fully understood the lesson. So the classwork helps to, to evaluate your performance. So it's also a means of reminder of what that has been taught. All right. Thanks for being part of this online class. So thanks for watching and learning with Peter Course Education Community. Stay well, take care of yourself. See you in the next class.